All right, welcome back to lecture number 2 of module number 1. All right, last time we said fluids are cool. Let's get excited. This time we will now answer the actual most basic question that coming away from this class, I hope you can answer, which is, of course, what exactly is a fluid? We're saying, all right, we're in fluid dynamics, but you say, hey, wait a second. In physics, in 10th grade in high school, I learned that there were 3 phases of matter: a solid, a liquid, and a gas, and I don't see fluid in that list. Well, that's great. In fact, fluids, according to physics, is a liquid or a gas. That's a physics definition, but still, if I sat you down and asked you, what is a fluid? Tell me in your own words. You can't just say a liquid or a gas. You gotta give me a more basic definition, a more mechanical engineering definition. So let's do that. Let's differentiate between a solid and a fluid. We're gonna do it in words and then in pictures. So a solid, if you apply a shear stress, it will resist that shear stress by deflecting a little bit, and then that deflection is enough to resist the shear stress, a static deflection. So a solid resists a shear stress with a static deflection, static meaning stationary. So it deflects a little bit, and then that is enough to meet the shear stress and counteract it. A fluid, however, does not do this. A fluid, the most fundamental definition is that a fluid cannot resist a shear stress. Just can't resist, which means that when a shear stress is applied to a fluid, it deforms continuously. Where our solid, let's draw this out. So here's a solid. We're going to draw it as like a cantilevered beam, because I feel like that's what they're always doing in those solid mechanics classes. So let's say this is a beam where we've got no gravity. So there's nothing pulling it down, right? Now we're going to apply gravity to this beam, and it is going to deflect, right? That's what happens if we apply a force to the end. Then our beam is going to deflect a little bit. We've got shear stress inside of this beam. This is just a little cross section, right? We've got shear stress, and the solid meets that shear stress by deflecting a little bit, a static amount, right? Here was our initial point. We've deflected some value, and then we stop deflecting. A fluid cannot do that. All right, so we're going to look at the most basic fluid anyone can think of, water. That's not how I wanted to draw that. Water. So here's our water. I can't draw a cantilevered beam of water because that's just not how it would be. So here's our wall like we had here. And this is, again, our no gravity situation. As you'll see in next lecture, water, when it is exposed to a zero gravity environment, will actually form a ball. Very cool, because the surface tension is dominating without gravity. So that's what's going to happen without gravity. Now, if we apply gravity, so we turn gravity back on, well, our solid deflected a little bit. That's how it met the shear stress present in the fluid, right? Well, when we turn on gravity and we've got forces pushing down on this water, and therefore shear kind of going throughout, then it's not going to deflect just a little bit. Instead, what we're going to do is actually draw a nice little bowl right here, and our water is going to deform. It's going to deform until it forms a little puddle just at the very bottom. So it has deformed continuously until it reaches a point where there's no longer shear stress acting on the fluid. Okay, now if we look at just a block of fluid, inside what we've got is fluid, and on all sides it is simply in compression. It's got pressure pushing in from all sides from all the fluid around it. Okay, so a fluid will deform continuously until the shear stress is gone. All right, so that's what makes a fluid a fluid. Let's talk a little bit more physics now. So that's, an engineering definition because we're looking at behavior from an engineering standpoint. Let's look at a physics definition. So according to physics, a liquid consists of some close packed molecules. And this width, that's my shorthand for width that I will use often. And those molecules have a strong cohesive force, something that is binding them together. Okay? And kind of the paramount of a liquid is that it retains its volume. So if I've got a container, and if I filled that container up with water halfway, then it is going to stay halfway filled with water. The water retains the volume it's been given. Now, counteract this with a gas, which is a group of loosely held molecules. Molecules with, you guessed it, a strong, weak, cohesive, that's an H, force. Okay, and a gas will expand to fill the volume it is given. So here is yet again our cup thing, and instead of water, you put some air into there, and you filled it halfway initially, but you really didn't because there's no way to fill it halfway. The gas just goes in and continuously fills the space. If you add more, then it just causes the pressure of the fluid to increase. If you add more liquid here, it causes the total volume to increase. Okay, so that's the difference between a solid and a liquid. A solid and a fluid, and then amongst our fluids between a liquid and a gas. But just like anything else in life, there hardly is black and white. Do we ever have a solid and a liquid? Well, sometimes the line is blurred. Although we will technically be in one true phase, solid or liquid or gas. Sorry, this should be solid and fluid. We can still say some things might be a solid, but act a bit more like a fluid. Like, for example, asphalt or lead. These are solids because they resist a shear stress with a static deflection initially. But over time, they begin to flow. And so these are solids technically, but they're called amorphous solids. Lacking an internal structure, they are able to flow very slowly, like a fluid. Likewise, there are other fluids, things like colloids or mixtures. Specifically, ketchup is a famous example here. That are able to resist shear stress below a given value, so below a threshold. So like ketchup, if you turn it upside down, nothing happens. You gotta shake it. You have to induce shear stress in the layers of ketchup fluid layers in order to get it to flow. So it's kind of like a solid, and then it turns into a fluid. All right, so that's what a fluid is. Now let's talk about where, you know, engineers and physicists are going to disagree. Oops. Sometime my pen will freak out, so please forgive me. And that is, in this class, we need to always have a continuum to use the equations we're developing. You say, continue what? And that is a continuum. A continuum is where we consider ourselves to have. This doesn't necessarily mean this is what we have, but we are thinking of ourselves as having an uninterrupted single material that has continuous properties. All right, so let's look at what a fluid really looks like up close. It's a bunch of molecules, right? These could have some bulk motion in one direction or be moving randomly. And that's what a fluid really is. But we don't want to bother trying to model how every single one of these little guys is going to move around and try to predict behavior that way. That sounds awful, like you'll get weird math. So instead, we're going to say, this is not a bunch of little balls. Instead, it is one solid thing that's not a bunch of little tiny molecules. It's just a continuum. And it has continuous properties throughout. So the pressure here is the pressure here is the pressure here. Okay, now this works if you have a large enough chunk of fluid. But if you only have, you know, well, how many is this? 1, 2, 3, 4, 5, 6, 7, 8. If you only have 8 molecules of a fluid, it's not going to act like a fluid. You got to consider each one individually. So the kind of line we draw is that the geometry our fluid is in must have a volume that is greater than 10 to the negative 9th millimeters cubed. And then we can assume a continuum. In this class, we will always have a continuum because that is just nasty if you don't. Okay, so that's kind of an aside. Let's move on to kind of another topic related to fluids, especially for engineers. You know, a fluid problem, usually we're trying to predict behavior. We're trying to make a model and predict something that's going to happen. And a key to prediction of fluids, and often the thing you're trying to predict, is the velocity field. Okay, let's define it and then draw a picture. So in words, the velocity field is just the velocity of a fluid, a known fluid in a kind of a geometry we're trying to solve, at any point in the fluid. Okay, so we know the velocity of our fluid at a specific point. So if the fluid at this exact point is moving in this direction, and we know it for any point in the fluid. Okay, before we draw it, you will recall that velocity is a vector, which means it has magnitude and direction. All right, let's put this into pictures. Consider a fluid that is flowing between 2 parallel infinite plates, because that's possible. Okay, so we've got these 2 plates that extend forever, and flowing between them is a fluid going, we'll say, this direction. Okay, we're going to define a coordinate system. We'll do this in a different color so things don't get messy. All right, we'll say this way is X and this way is Y, because that gives us the right-hand rule Z, I think. When I first made these notes, I didn't do the right-hand rule. Shame on me. Okay, so we will define a point. Here's what I mean by a point. Any spot. And we'll just call this point P. Very original. And this would be at the location XP, YP, and ZP. Okay, we're going to draw a box around this thing. We're going to go to our next slide and kind of zoom in on it. So here is our point P, which is again at a specific spot at XP, YP, and ZP. Okay, and we can draw the vector of the fluid direction. So this vector is pointing the way the fluid is going, and it has a length or magnitude to designate how fast the fluid is going. So at that point, which direction is the fluid moving and how fast is it going in that direction? And we're going to designate this vector as a V with a line over it. And so this would be the velocity at our point P, which is at XP, YP, and ZP. So we can write this using vector coordinates, and I'm not too sure what your background is on vectors, to be honest. I'm still pretty new here. So we're kind of gonna take it slow. So we've got, the way we're gonna write this is the vector V at any point XYZ we can write as a scalar, which is just a number, not a vector. So like 5, that's a scalar. So a scalar u, which we have u at any point xyz in the I hat direction. You say, what is I hat? Well, I hat is a unit vector pointing in the x direction that has the magnitude of 1. So here again is x. I hat is a vector pointing directly along x, parallel to x, and its magnitude is 1. Oops. Its magnitude is 1, and so we can use it to indicate direction without affecting quantity because it is 1 long. Okay, so what this does is this tells us what our speed is in the x direction, specifically in the x direction. That doesn't mean our fluid is going only in the x direction, but tells us how fast it is going specifically in the x direction. Okay. Next, we have v x y z times j hat, where j hat is the unit vector in the y direction. All right, so going back, now here's j hat right here, pointing directly in the y direction with a length of 1. And then this is the scalar, or the value that tells us the fluid speed specifically in the y direction. We're going to draw a cool picture after we're done writing this to help you understand if you're getting lost. Okay, we've got one more, w, oops, which we can define at any point x, y, z in the k hat direction. Any guesses on which way is k hat? That's right. That is the unit vector pointing in the z direction. Okay, where w is the fluid's speed specifically in the z direction. Okay, so to avoid confusion, let's break it down a little bit more. This is really important, so I want to make sure we get this. All right, so we're going to draw our axes again. All right, so here is x, here is y, here is z. Okay, now we're going to draw a vector. We'll draw it in green. So this is our actual vector of the fluid's velocity. So it's pointing the way the fluid at that point is moving, and its magnitude is how quickly it's moving in that direction. So we're going to draw it like this. Okay? So our fluid at point P, which is here, is moving in this direction, and it has a magnitude equal to the length of that arrow. Actually, we'll do this now in red. So now what we're going to do is we're going to break this down into its 3 different components. Okay? So we're going to, this is hard to draw. So forgive me if I don't draw it well. So we dropped down in z to z of 0, and then we dropped down in y, so y was 0, and now we see that this is purely the component of that vector pointing in the x direction. So this would be u, and it's multiplied by I hat, because I hat, let's do this in blue, I hat is a vector pointing exactly in the x direction. So u gives us the quantity, I hat gives us the direction, and they are parallel. And I hat is 1, so it doesn't affect the quantity. Pretty cool, right? All right, let's see. Next, we're going to go down again with the no z part, but now we're going to go over so that we go to an x of 0. And we're going to go to this point. Now we can draw a line from the origin to there. This would be v, right? It's the velocity specifically in the y direction, and that will be multiplied by j hat, which again, I never labeled that. That's I hat. This will be j hat. Okay, now you guessed it. We're going to do this to show what w is. This is the tricky one to draw. Okay, we're going to go along until we get to an x of 0, and now we're going to go down until we get to a y of 0. And so now we've got this vector pointing from the origin to that point, and this is w. And it's multiplied by k hat to give it a magnitude and direction, where k hat is again the unit vector pointing up in the z direction. And so what you see is v, which is this vector, being the actual direction and velocity the fluid is moving, is just going to be equal to the addition of these 3 smaller vectors, which when you add them together, you do u I hat, so u I hat. And then when you add vectors, remember you connect them tail to tail. So u I hat plus, you add it to the tail going towards the end. So plus v j hat, and then we add one more vector plus w k hat gives us v. So that's just a visual depiction of how we can break down v into 3 components, each pointing in a specific direction. This will make it easy for us to break down our governing equations into a coordinate system using x, y, and z. But for now, all we have to understand is what this vector represents. Okay, but why do we really care, right? So we need, what's going on, Penn? We need that velocity vector, v, x, y, and z, in order to find the pressure at any point in our flow, to say find the stress the fluid is putting on the wall, to find, let's say, the flow rate of our fluid, or to find the energy inside of the fluid. We're going to spend a lot of this class on chapters 3 and 4 in your book, which focus on finding v. They say find the velocity profile for known geometry and known boundary conditions, which we'll define all of that later. But we want to find those so we can really extract this useful information. All right, we've got one more thing to do in this lecture, and then we will move on. So the velocity field is cool, and one really cool thing about it is we can visualize it, right? So the velocity field, in theory, tells us which direction and how fast the fluid is moving at any point, anywhere in the regime, in the geometry we're looking at, like say in a pipe. We could look at any point. If we know the field, I could tell you how fast the fluid is going and which direction it is moving in. Okay? So there are a few ways to visualize this. There are things called streamlines and path lines and streak lines. All right, a streamline. This is getting a real technical, but we'll draw a picture. So a streamline is a line that is always tangent to the velocity vector at a single moment in time. Yeah, let's draw a picture for that because that sounds real confusing. Let me get these notes spread out. Okay, so streamlines. Let's say we have some flow, some geometry, and inside of it, we've defined some points. So here's a point, and here's a point, and here's one. These are all points inside of a fluid. And we know the velocity field, which means I can draw at each of these points a vector giving the direction the fluid is moving and how fast it's going. We're going to say that at each of these points, the vectors look like this. Now, the cool thing about a fluid is it is mass, and mass exists and can't be created or destroyed, which means that the velocity field, you know, this is important. The velocity field must be continuous. Mostly. When we get into compressible flow, that can not be true. But for now, we will say that. So we're going to say the velocity field should be continuous, which means we should be able to draw a line connecting all of these vectors together. So we're going to draw it like this. So see how I've drawn a line that is tangent everywhere to the velocity field. I'm sorry, to the vectors. That is a streamline, a line that's always tangent to the velocity vector. And this is for a single moment in time, right? So this is a snapshot. Say we're looking at flow around a ball. And so we've got kind of this going on. And this is that line, that red line I've drawn down here. And so this is for a single moment in time. We visualized this. And so we're visualizing, when we draw these kind of lines like this, going around something, you're drawing streamlines. You've been drawing streamlines since you were a kid. Okay, those are streamlines. What about path lines? Okay, well, a path line is the actual path which is traveled by a single particle. So let's visualize that. Path line. All right, so if I've got an actual air molecule at time equals 0 at this point, then let's say several seconds later at time of t0, it is over here. I could draw between these points a path line. Oops. Which represents the actual path traveled by this specific point between these two locations. I think you're probably starting to wonder, well, isn't that the same thing? You just wait. You're getting ahead of yourself. So let's go finally to streak lines. A streak line is, I think, definitely the most confusing. That's a line which is passing through all particles that have passed through a point. Okay, so these are a little confusing because streamline is specific to a single moment in time. You can only visualize a streamline for one moment in time because the velocity field can only be depicted at a single moment in time. Path lines are used to depict really what's happening to the velocity field over time if it's changing with time. So to visualize a streak line, all right, let's say we've got a pipe. Maybe it's a hose. My 5-year-old has once again turned on the hose. And initially he turned it on really, really fast. He always does. So the water is shooting out really, really far. And so let's say we had this particle and it traveled some distance over some period of time. But over time, I yell at him and he starts to turn the hose off, which means the particles begin to drop. Okay, and so these kind of represent particles which left a specific point at different time, at different periods in time. So at time of 0, this particle was at this point. And then at time of delta t, let's say this particle was leaving this point. At time of 2 delta t, let's say this particle was leaving that point. Time of 3 delta t, we'll say this particle was leaving that point. So they're all particles, and what they have in common is they all pass through a common point. Remember, that's kind of the key word here. A line passing through all particles that passed through a point. So we could draw a line between them. This represents a streak line. Honestly, we don't use this one very much, so I wouldn't worry about it too much. Okay, now, at steady state conditions, what does steady state mean again? It's an important word. Steady state, which I'll abbreviate SS, means there are no changes with time. So the flow field looks the same 10 seconds ago as it does now as it does 1 hour from now. Or that the pressure and all of the properties are not changing with time. So if that's true, then you could see how all of these things would look the same. Right? The streamline is going to be, any particle following this streamline is going to follow the streamline if there are steady state conditions. Right? So that'd be a path line. So the path line will be the same as the streamline. Now the path line will be different if, say, between time 0 and t0, maybe the pressure on this side went up, causing the flow to accelerate. And so the path line will not be the same as the streamline because we do not have steady state conditions. But as long as everything remains the same, all the properties remain the same and don't change with time, then the streamline, the path line, and the streak line will all be the same. They will look the same. So a streamline will be equal to a path line, which will be equal to a streak line. Okay, again, that is only true for steady state conditions. All right, honestly, what we will use in this class are streamlines, especially when we get to CFD. We're going to use streamlines to visualize flow. These days, you probably see more kind of like colored plots of the air around an object in CFD. Those colors are like streamlines, but represented in 3D by using colors to represent velocity instead of a line. Okay, great. Let's move on to the last lecture for this module about fluid properties.